Okay. Okay, so okay, this is all that we have actually covered. And so in Transformer, we started learning about the self-attention, and this is the logical, progression of deep sequence learning. And there were issues with the RNN, LSTM, and Transformer kind of has resolved all these issues because it's kind of not recursive, like it is everything you feed at once. So once you are feeding everything at once means you can do parallel processing. But the challenge is that you say a lion ate the goat, okay, and if and the goat ate the loin, so it has all the same words, okay. So how is the transformer going to know? Because sequence is important. The sequence, why the sequence mining? Because the sequence has the basic understanding of the sentence. Like if you just disturb the sequence and just rearrange the words, they may just completely change the meaning of the sentence. So up till now, what we are learning is like it is focusing on words. Okay, this self-attention, as you can see, is just focusing on word. So if you can even say the other bank swam across the river to get to I, okay, because it has the same word, so it is almost going to give you the same answer, the same result. Okay, so we will come back to this, that why you can do, and this must be like the guy must be very, very smart, okay, and must have like kind of blind belief into this learning process. That's the second thing which I could only understand, that how can you just put a sequence, okay, into a neural network where they are just words, and all the entire algorithm is just working on words, that how they relate to each other. Okay, so as we know, the self-attention is that how these words they relate to each other. Okay, because it says that a word is known by the company it keeps. So word, if a bank, and then shall know a word by the company it keeps. So the bank, and if you say bank and drove and road, so it will be financial institution. But if a bank you swam and across the river, then you know it is the bank of the river. So context really matters, and this is the essence of large language models. This is the essence of transformer as well. Okay, so the context is important. I showed you this, that if there is actually a flood and there is a bank, and then you can perhaps say that I swam across the road or the river, so to say, to get to the other bank. So the self-attention is simply, it is the mechanism that weighs neighboring words to enhance the meaning of the word of intention. It is actually, as we have learned, that all you are doing is that once you do embedding, so the words are replaced by vectors. So if words are replaced by vectors, so there are no more words, they are vectors. So can you just create a vector that has the essence of the words which are with it, which are associated with the word? So that's totally the purpose of this whole thing, is that every word, once you do the embedding, so every word is a vector. Okay, embedding is all about converting every word to a vector. So every word is a vector. So a vector, another vector, another word, another word, another word, another word. Okay, these all are vectors. So this is called the embedding. So embedding is kind of a function that take an actual token or a word, we also call this a token, and converts it into a vector. Okay, and vector may have very high dimension vector, 512, 300. So a very large dimension vector, because it is capturing the entire dictionaries, and not only that, it also has to be in a space where it relates to the words which kind of relates to this word. So that's why they have many parameters. And you cannot really, the people who are working in an explainable AI, they may just go and find out what each parameter means. But still, people are not really able to figure out that what each parameter. But once they look at a word, which is a similar word like king and queen, they will find several of those fields in these 300, several of these numbers in this 512. They look similar to each other. So means that it's like they have learned in a way that they are obviously in a close proximity. So all these numbers are similar. So that's why you get a good dot product. So self-attention is that you have this bank, it relates to river and swam. So somehow I got to color this bank or the vector so which should have the essence of the river and swam as well. So once the large language model feed in the bank, it is no more the original vector. It is the transform vector which has gone through the transformations. And now this is the vector which guaranteed that it would have understood that this is a bank, it is a noun, it is actually a financial institution. And then it will able to just generate because you have fed it to a number of sentences. So contextual information is important, and that a way to represent the contextual information in a sentence, in an image, or in any other thing is the self-attention, that you are just paying attention to things so that you can just make their relationship with the other in the figure. So we know that in all natural language processing, no machine learning algorithm can kind of work on words. Okay, if you try to, it'll become very difficult for a machine learning algorithm to work on actual sentences and actual words. So you got to somehow tokenize means that you have a word I here, a swam here, okay, across here, almost a word is a token, and then you vectorize it. So this is, and today we will also study a little about the graph neural networks. They also precisely do the same thing. Every node in the network has to be converted into vectors, right? Through the same process. They call node embedding, word embedding, because once a node becomes a vector, and then all the machine learning algorithms are almost the same, that you use SVM, use whatever you want to use it. So that the most important aspect, even in GNN, is how in your Facebook friends, okay, your Facebook friends how can they be? Every node becomes a vector, and once you plot them, like you plot these vectors, those who are your friends will be in one space, and those who are friend of somebody else will be in another space. So that's kind of a magic, that once you kind of embed, and once the way you optimize, that all the similar nodes, their vectors will have large dot product, high dot product values. They will be occupying the same space. And once you have converted them into vectors, then everything is possible. The entire, the machine learning, that's as we are doing it here. So we learned that usually this one hot encoding is not really good because it just fails to capture the essence of a word. And because all of these, if you take dot product, you always going to get 0. Element by element, if you multiply, you're always going to get 0. So that's an issue. So that's the reason, that similarity. We have algorithms that learn every word and its neighbors. So all the tweaking and the parameters you do, and then you find out that banking vector is very close to monetary, because these are two related words. Right? So all the words which are same would be need and help and take and get and continue to keep and make, they will occupy the same space. So this is the embedding that you do. And embedding is not new. Like it was Word2Vec and Glove, they were done many years back by 2030. And that's why Google will help you to find the next word. And once you're typing in Google, it just start giving you the next word. Even in WhatsApp, you are typing, it just keep giving you the next word. So these have been there, and this is how the word to vec basically is created. That you have all these sentences, and all these sentences, if you are trying to figure out into the word embedding of into, you need to know who its neighbors are. Okay, so you say you have a window, and you say given into what is the probability of banking, what is the probability of turning, and then you span the entire whatever documents you give to Word2Vec, maybe an encyclopedia, maybe the entire data on the internet, so whatever, and then it will have probabilistic distribution, that this is the probabilistic distribution, that if I am into, the most probable word is this, then this, then this, then this, then this, then this, then this. So they get the probability distribution, that, and this is without any regard to the entire sentence. Okay, it is just the word, and whatever data you have fed, what is the probability distribution of the words which are coming. For example, into, if every time banking comes, it means its probability is 1. Okay? But half of the time banking comes, when we say into banking, so it means probability 0.5. It's very simple to find out these probabilities, and then the parameters, the model that would actually, so the same thing, that you got to have a likelihood function which would kind of maximize this probability, and this is over every word in your dictionary, okay, every word in your corpus. You do this, and then you have these vectors. Vectors are what? Theta. Theta are the parameters. So whatever learning parameters you have, you train them, and then it becomes your vector. And so the very first thing in deep learning and natural language processing, you embed your words. So this is called word embedding, and every word gets converted into a vector, and so you have this vector, and still this vector again does not have the sense of the context of the current sentence in which it has. It may not be the most probable word that is following this. Okay, so the context becomes important. So this is, up till now, the context is not there. It's just whatever it has learned. It is just, it has those probabilities, and that's how it is pointing to the other words. So if remember, I showed you.
Tokenize and vectorize.
जी, tokenize means just a word by word आपने अलग अलग कर लिया. So every word is, you just say word, word, word. So if you have a dictionary, so let me first show you this. So tokenize का मतलब सिर्फ ये है कि you separate every word, and every word is then a number, an index into your vector space. Like this is vector number 299, this is vector number 9, this is vector number 10. Okay, so for example, here you see a 3-dimensional space. So if I just put my cursor on any word, for example here, okay, this is boom, for example. So boom has some index, that it is at this index in this dictionary, and then you see from the similarity perspective what are the other words. Okay, and here are growth, bubble, explosion. So you can just actually point to any artillery, for example. So say artillery, armored tanks. So you can just see playing with this, and this has like so here are like the probability distribution of 512 words with manual, tools, programmer, documentation, handbook, So all these are, and here the dimension is 200, and there are 10,000 words. So every word, so now you perhaps understand that it's an array where index is 0, 1, 2, 3, 4, 5, 6. So it is where you have so you say this is word number 212, this is 11, this is 219. So these are the tokens. Okay, the bank is let's say 512. So every word you have now, every word in the dictionary, you have it in a table, where table gives you a number that, and then a vector. Vector is a 300 dimension or 512 dimension or some dimension vector. Okay, so that's what it is, that you have the tokenization and then you have the vectorization. Now this is a vector, so now you are no more into this space. Now the words and are not important for you, and these are the vectors, because it's a vector that gives you, unique power to just modify it. Okay, you can modify the vector. So I've shown you, this is the link. I would urge you to go and play with this link, find out, just point to any word and see that how beautifully it has captured the word with its relevance, and how it basically built that. So now what you got to do is that every word converted into a vector has to be transformed into another vector for some reason here. So converted into another vector y1, y2. So every vector is converted into a vector of same dimension, right? Vector of same dimension, but now every vector has the essence of its neighbors, so effect of its neighbors, so that as it is moving up the layer in a large language model, it has a lot of understanding of its context. Okay, so that's what the idea is. So, and how you find out, so one is we call just self-attention, simple self-attention. Okay, so it is easy to compute, simple self-attention. You don't need to have any weights, parameters which you got to train, because word2vect has already done that for you. Word2vect has already done that for you. So most of the work has already been done of the training and parameterization and everything. So simple self-attention is very simple to compute. It is only that you compute dot products. Those vectors which are closer will give you a high value, and those vectors which are away will give you a low value. So dot product is magnitude of this, magnitude of the other vector, and the cosine of the angle between them. Okay, so this is how you compute the dot vector, and those vectors which are close to one another, their dot product is going to be big. So that's how what you do, you get for simple attention, self-attention, you compute the dot product. So what you do is this vector dot product with all of them, then you take this vector dot product with all of them, then you take this vector dot product with all of them, because once you are doing this, you are going to get a matrix. Okay, so this is v1, v2, vn, and here is v1, v2, vn. So vn dot product with vn, vn dot product with v2, vn dot product with v3, and v2 then dot product with v1. So obviously here you are going to see the perfect dot products, because they are the same vector. So your interest is actually in the other, but you are going to see v1 v1 transpose, v1 v2 transpose, v1 v3 transpose. Okay, because one way to take dot product is between two vectors is keep one vector as this. Let's say it is 200 and let's say 300 rows and one column, and then you have another vector and you take its transpose, and it becomes 1 into 300. So 300 you get 1 into 1, you just get one number. Okay, so you get the dot product of this. So you will find out once you're taking the dot product of the very first layer. So the very first layer, there are no weights, and this is just a simple dot product attention. So you're going to see a matrix like this. So this is where you have all ones. So all ones, highest score. And then those words which are related to each other, you will find that they are more across and bank. So you will find out they are like, here is a swam and the river. So you will have higher value of the dot product, because word2vect, we have already seen word2vect has actually captured this thing, that once you say river, it will show you the bank, it will show the swam, it will, so it will show you all those things. So it means that it basically has already captured this, and so it will show you that yes, I have now this word to vector. Okay, so you are going to see a matrix. Okay, so this matrix is you call the first element as S11, S12, S13, S14, and similarly last one SN1, SN2, SN3. Okay, so this is how you basically represent these vector. But usually we like to see probabilistic way of looking at once you have so many numbers. So you want, it's better that these are the probabilities. So probabilities, for that you do softmax. Softmax is where it will convert this entire matrix into probabilities. Okay, so you normalize and softmax. Softmax is that you take exponential of Si and you divide it by j is equal to 1 to n. So you are computing I and j, all j exponential of Sj. Okay. So for example, if you are doing W11, so 1 with 1. So okay, so you have already computed this, you take its exponential and divide it with all the exponential so that you get a probability distribution. So these are the probability distributions. Softmax, always remember, would do this. Softmax operation is going to do this. Okay, so that once you add for every j, once you add all the weights, it is going to give you 1. Okay, so that's what the probability distribution is. So you like the probability distribution and you like this instead of just, because once you look at it, so you will see that it is how the entire relationship is probabilistically distributed, which has the major contribution, which has the least contribution. So so once you have these probabilities, and remember this has the essence of your first V1 with V1, and this has your V1 with V2. Okay, so and this is actually you are going to replace your vector V1 by Y1, your vector V2 by Y2, your vector V3 by Y3, and your vector Vn. So you had n vectors, and based on the self-attention, and as you can see, it has the essence of its relationship, this word relationship with rest of the word. That essence has come into now in this vector by having all these weights multiplied by their respective vectors. Similarly, the second word has now the essence of its relationship with all these words as you are again multiplying that. For example, it is not really related to W23 and this is 0. The probability distribution W23 is 0, so it is just going to multiply this with 0. This has very little contribution, 0.01, so it has very little effect of this vector getting into the V2. But let's say 2 and 1 are very closely related. Okay, so let's say it is 0.9. So it is going to V1. The Y2 would have a lot of effect of V1, and this is definitely 1. So it has 1 and 0.9. So it is 1. Let's say rest all the weights are 0. So it is 1 0.9 V1 plus 1 V2 is equal to Y2. So it is the sense of these two words. You are just coloring and finding another vector, which you can only do this in vector space. You cannot do this in the word space, that you cannot just create a word which has the essence of the bank and the swam and the river, so, and make a new word. You cannot do that. But the beauty of this is you can make a vector which has the essence of these three words into just one vector. So that's the idea primarily. You are way जी जी वालेकुम अस्सलाम
सर ये वेट्स किस पे डिपेंड कर रहे होते हैं वेट्स की वैल्यू किस पे डिपेंड करती है
जी जो वेट्स हैं इनकी वैल्यू डिपेंड कर रही है आपके डॉट प्रोडक्ट पे V1 dot product V1, V1 dot product V2, V1 dot product V3. So this is W11, W12, W13. सही है ना? तो इसका फर्स्ट वेक्टर का फर्स्ट एंड व्हाट इज अ वेक्टर इज वर्ड 1 जो आपका वर्ड सेंटेंस में पहला वर्ड था, ये दूसरा वर्ड था सेंटेंस में, राइट? सो द वर्ड्स कन्वर्टेड इनटू going through a process of the dot product and then changing into the probability distribution, so that once you add all the weights, it should be 1. So and that's what you do, you convert those numbers into a softmax. Passing it through the softmax, it will just assign them relative grading, so that you get a probability distribution of the impact of the other words into this word. Okay, that'll show you that how this, and there are many interesting visual tools now, because there is another like class, another group of people who are really worried about all this AI. So we'll talk about this explainable AI. Okay, so there is a whole field which says, no, I want to explain what is happening. Okay, so a little they can explain, but they cannot just explain everything. But still, there are so many things which are just happening. Okay, very little they can actually explain. But whatever little they can explain, they are just trying to get into the algorithms and trying to get an explanation. And this is one explanation which I am giving you. So this is easier to kind of, this explanation is easier to make. Now you have all these vectors which are the contextualized representation of vectors. Okay? So this is very good, because now every word has its context. So what we have done is, and this is answer to your question, scores by the dot product, and then you normalize, and then you weight original vector. Original vector से multiply करते हैं. So normalization is where you're doing softmax and dividing it by the exponentials, and so that you get converted into a probability distribution. So this is again answer to your question. So these are all the words, and every word into a vector. So you take a word, V2 is corresponding vector, take the dot products, these are the dot products, and then you normalize them by converting them into probability distribution, exponential of minus this number divided by exponentials of all these numbers, so that once you add them together, it gives you 1. Okay? So this is the distribution. And once you have this, now because now this is going to replace V2, so you have now these 3 numbers. Let's say, as I was explaining, that this word is very closely related to 3 but not related to 1. So it's going to have a 0, here you have a 1, here you have, so it will be perhaps 0.5, 0.5, because it has total has to be 1. Okay? So you just multiply and you get another vector. So this is the idea, that you get another vector by, so this is step by step, the same thing, that you have these vectors, these is its relationship with the other words in the sentence, and you get y2. Okay? So this is what you are going to get. But now comes the complication which nobody can actually able to understand and explain. Okay? So up till now there are no weights. Okay? There is no trainable parameters. It is just, you don't have, it means you are not even training anything. So it's not really a neural network, because there is no back propagation, there is no training. You get words, you convert them into vectors, you take the dot product, do the softmax, and so but now here comes the weights, the learnable weights, because now it becomes a multi-head self-attention. So the weights gets into the picture now, that where are the weights? So up till now there are no weights. So there are no trainable weights. These are not trainable. I hope we understand trainable. Trainable weights are the weights where in a neural network you have data, you pass it through it, and then if there is an error, you take this error and feed it back to the network and tune all the weights using back propagation algorithm, which takes the derivatives, find out the gradient, has the error. And so we have learned about that. The other thing which I want you to know is what type of dimensions we are like working on. Now remember, let's say I have the sentence I. दोबारा से बोलना पड़ेगा, वो सारा आपका वो scrambled kind of. So can you ask again? So what I am saying is हाँ जी, ये वो वेट्स ट्रेनेबल वेट्स नहीं है ये जी, आ रही है। मैंने कहा ये जो वेट्स थे ट्रेनेबल नहीं थे।
वो न्यूरल नेटवर्क के वेट से कंफ्यूज करी थी।
जी जी, नहीं 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 नहीं, ये वो नहीं है। जी जी, वो नहीं है, अभी वो वेट आने लगे हैं, ठीक है। सो दीज आर नॉट द वेट्स इन द न्यूरल नेटवर्क। नाउ वी आर गोइंग टू सी दैट दोज वेट्स विल कम इनटू द पिक्चर, ठीक है। फॉर एग्जांपल देयर इज अ सेंटेंस आई and it is, let's say, dimension d. This is the dimension d, is that the dimension of the vector, okay. Like is another word, again d dimension. To eat barbecue, so it becomes a matrix of n words, so n words into d. So there are n rows, every row means a word, and then every word has d dimension. This is the word embedding that you are using. It depends, somebody uses word to vec, somebody uses glove, somebody uses others, and even there you can have have your dimension, which you can just ask that what dimension of the vector that you want, okay. So this is the size of your input vector, so input matrix I should say, it is d by n, okay. So what you are kind of doing is that you have all these vectors which are d by n, and then you are multiplying it with itself. The transpose of itself will give you the dot product. So you are multiplying it with n, so this is d by n, and you are multiplying it by itself, becomes n by d once. So n cancels, so you get a vector, sorry, n by d, and this is d by d, so you get a matrix n by n. This is the matrix we have. इसने गलत किया d by d, we get a matrix d by d, oh sorry, n by n, ठीक है, sorry, ठीक है, n by n. So we have seen a matrix, like if we are using 6 words, so you are going to see an attention matrix which has 6 rows and 6 columns, a square matrix, okay. So you are going to get a square matrix, and this square matrix then you take, so this is the square matrix, then you take and again multiply it by, so this is n by n. Why I am doing this, I'll tell you in a while. N by n into n by d, which is again you multiply with the same matrix, because now you are going to transform this matrix. So n, so you get an n by d, which is the original n by d matrix, okay. So let me just, because this is important. So you have this n words, every word has d dimension, okay, and you multiply it with its transpose to get the dot product. So it is d and n. So this is n by d into d by n. You are going to get a matrix of n by n dimension, okay. But important is the large language model is just doing matrix multiplication. Many, but matrix multiplication, matrix multiplication, matrix multiplication. So it's all linear algebra, okay. This is how we started our course. As the linear algebra becomes important, okay. And this is what is the self attention matrix, self. And once you do softmax also, so you see a probability distribution here, okay. So it's a probability distribution, everything is summing up to 1, okay. All these weights summing up to 1, so it has contribution. And now what you do is you take this and multiply with the same vector. If it is x, x transpose, and self attention A, and then x.
Excuse me, sir.
जी
सर ये जितना आपने सेंटेंस बताया कि आई लाइक टू गाती हूँ, तो सर इसमें इन सब वर्ड्स की डायमेंशन सेम है
जी, हर वर्ड क्योंकि वेक्टर है ना, तो उसकी डायमेंशन सेम रहेगी. एवरी वेक्टर हैज द सेम डायमेंशन. वर्ड में हैव डिफरेंट नंबर ऑफ, ये बहुत अहम बात है. अ वर्ड में हैव डिफरेंट नंबर ऑफ वर्ड्स, बट वंस यू एम्बेड इट in a vector space, the dimension of the vector will remain the same. Okay, now it becomes a vector of the same dimension. Every word becomes a dimension of the same dimension vector. ठीक है? Like this one which I showed you earlier. वो जो मैंने आपको एक I think so the website, so you should go and look at the link, and all those vectors are of same dimension. Okay, and that's the whole purpose, because and that's why it becomes so convenient to use a GPU or TPU to train the models. ठीक है? अच्छा, अब क्या हुआ कि this is where, so this people could just explain that, but now they use to get to multi-head attention. So they want, because different words based on the context may have different relationship. That is what I was explaining in the previous class, but we'll spend more time today also. So they may want to look into different aspect of the same sentence. For example, yes, it is important for this sentence that it is important for me to know that the banks and the swam and river a bank are important, but for the sentence understanding it is also important I swam, not Jamil swam, or so I swam across the river. I becomes important, other bank becomes important, another perspective, because sometimes you have to learn the verb, where is the verb, because sometimes I love is a noun, is a verb, okay, and Pakistan is my love becomes a noun. So many has to be learned from a sentence to have a completely 100% understanding of the context, so that it start generating what you actually want to generate based on the prompt that you have given it. It has to just understand everything about the prompt. Okay, so that's why the self-attention, just saying that the bank and the river and the swamp, because they are closer into word to vect, so I am done. No, you are not done, because then if the next sentence is that there was a news in the newspaper that somebody drone, or something which relates to I, so it has to kind of learn that it is that I which I'm going to just explain in a while. So because of that, now things start getting messy. Okay? And what they did, they said, let's just have a trainable parameter, so that it start looking into different aspects of the relationship based on this sentence, different part of the relationship based on this sentence. And they say, let's have, because now you're going to train this on all the, for example, all the data on the internet. So let's have a matrix which are the trainable weights. Trainable weights. So these are all trainable weights. Okay, so trainable weights, and the concept of query, key, and value. So that this is the self-attention paper brought this aspect that the same matrix. Remember this matrix? It was n by d matrix. Has to be kind of changed so that it looks like a query, as you do a query in the database. The same matrix looks like a key, as there's a key in the database. And the same matrix look like a value that once you query, so usually you have, as I gave you an example, that you search for CNN. So this is your query, that you on a Google, you are searching for CNN, and the CNN is going to show you the CNN, the news channel, and somewhere it says this is CNN, this is the convolutional neural network. So definitely based on the context, you are more related to this. So you click here, you get the CNN, information about the CNN, this becomes a value. Okay? So the key, the query, the value. So and this is where people cannot really explain that how this thing is actually happening. So this part is explainable, where you have this softmax and everything, and people are still trying to struggle that how these weights kind of are making this matrix, making this into a query and a key and a value. Okay, so that's the concept, that you have a query and a key and the value, and you are going to transform this, and they are going to be matrix multiplication, and then almost the same thing. Then afterward, then they are the same things, and ultimately you are going to get these transformed values, and you are going to have multiple layers of these weights, multi-head, multiple layers of these weights, and you just train them to just get what you want to get. Okay, this is called the dot product attention. Now we have come, and they also, once they are doing a dot product, they also divide it, because dimension, as I mentioned, that dimensions may vary. So they want to just normalize it, so that once you're computing dot product, you're multiplying them together, you must not get big numbers. So there will be problem, because you will learn, and perhaps once we train this LLM, you quantize the weights. You say, I want to keep 4-bit or 8-bit. The reason is, once you have like 16-bit numbers and they are multiplying, so they grow, and then the computation becomes very expensive. So sometimes you are computing the dot product and you divide it with the dimension of the vector to normalize it. That's what this paper has done, that it divides. And this is the formula. This is the self-attention formula, where now you have this Q. So Q is something, once you have after the transformation, once you get the query, it is Q. Okay, and once you have K, and it is again going to be N by D. So if this is N by D, and I want to get an N by D, my weights will be D by D. Okay, so this matrix, sometimes you write it as WQ and WK and WV. These are the weights, and as you can see, like it's a 512 by 512 dimension, 3 matrices just for single head attention, and these are all tunable weights. Okay, these are the weights that you are going to tune, and then you get these matrices, because this is where you are computing the softmax of. So we have already seen this. You take Q, you multiply it with the K transform. Previously Q, K, V, they were the same matrices. Now they are no more the same matrices. Okay, they are the different matrices. So you multiply them together and you scale it. So this is the scale dot attention, and then you take the softmax of it. Once you take the softmax, again you are going to get an N by N matrix. So this is an N by N matrix, and you take this N by N matrix and you multiply it with N by D matrix, which is V. So you are going to get an N by D matrix, which is the same as you started with. You started with here N by D matrix. So this is the transform matrix. Now this is what the self-attention is, that there is a transformation, where you have these all linear layer of weights. So this is where it says GG.
सर ये जो की क्यूरी और वैल्यू है, सर ये एक तरह के सिस्टम को वैसे पता चलता है कि ये इनमें डिफरेंशिएट किस बेस पे करता है
जी,
और दूसरी चीज कहते हैं ये नंबर्स के फॉर्म में होता है.
yeah, this is just a matrix. देखें, this is a matrix, this is again a matrix, this is again a matrix. So these all are the matrices, and अभी थोड़ा सा हम एक दो slides करके फिर then I'll perhaps able to explain. But remember, this is not really explainable, that how it just works. Whatever was explainable, I have explained. That this is explainable, what the weights are helping them, and this is where you just have to trust that this thing, which is a black box, which has billions of parameters, they are just going to be trained so that you get what you want. Okay, and why they are doing this, perhaps that's people are still struggling to figure out what are they doing, so to make something a V and a Q and a query. Okay, so here is the idea about query. you do CNN, and you are going to get, these are the keys, okay? And then, so the key 1, key 2, key 3, and this is resembles the most with, and some resembles a little, you know, you must have done this, right? Some resembles a little, some resembles more, and then you have to go and see the values to find out which are related to this. So in classical sense, okay, a query will only match to one key, so you only get one value. This is just the classical database type of a query, that you give a query, it is going to match with a key, is going to give you data. But here it is that your query is going to match a little with every key in your system, and by different weights, and this is where the weights come into picture, that is going to match with every key, and so you get values. So you have these, all these weights that you get, so all these are the weights that you get, and you say, and this is what we have been doing all along, that you have all these weights, so you have W11 into V1 plus W12 into V2, and so you multiply them with the vector to get the answer, the value, the output that you get, okay? And this is, we have already seen this, that you have queries the same, keys the same. First of all, first time, your data is going to be the queue and the key and the value. So these are, if they are T or N, so this is what, and we have also seen that what the softmax will do. The important is this matrix which I told you. This is, it is here calling K, but in many they call WK, WQ and WV. These are the trainable weights. This is a D by D dimension, this is D by D dimension, and this is D by D dimension. This is what you trained. And you are multiplying it with your vector initially, which is X. X is your vector, which is your input, okay, and which is N into D, N into D, N into D. And in this paper, instead of N, it is saying T. They are T tokens, but the same thing, okay. And this is, every word is D-dimensional. Every word is D-dimensional. That's why it is multiplying every word with this and converting this into another word. And these are the weights, so you get, and this is where these matrix multiplications are. So if you do the softmax, this thing, if you write the softmax, where, remember, softmax was that you have this X into Q will give you the new query, and then this X into K will give you the new key, and you take its transpose, and then you take the softmax. So many, just vector to vector multiplication. That's why it shows you vector multiplication, vector multiplication. So if you open it up, you find out, oh, I have to multiply all these matrices together to get a value which then take the softmax, and this is, remember, it is N by N or T by T. And then again there is a matrix multiplication, okay, again matrix multiplication, and then you get an output which is T by D. Okay. So this is what the, so the matrices and the multiplications and in their algorithm, once they show you the figure, they show you, whenever they show you the, so they show you matrix multiplication. This is Q, this is K, this is V. So first you multiply them, scale them, and mask is in the decoder. Then you take the softmax, here comes all the weights, and here is the V. Again you do a matrix multiplication to get Y. Okay, so matrix multiplication, matrix multiplication, matrix multiplication. So a lot of matrix multiplication in a large language model, mostly just doing matrix multiplication. That's why it is also possible. Otherwise, I was just looking at ChatGPT 3.5 would have taken 351 years to train. 300 on one GPU, 351 years. So you can imagine that without the way they have formulated this whole thing, it becomes so convenient because of all matrix multiplication. And this is the reason that I'm really motivated to do this on FPGAs, just to have localized solution, further optimize this whole thing. So we know that this is what it is, all these matrix multiplication, and would give us the.
These matrices are actually the whole web page words. जब ये k वेक्टर
जी
बनता है, ये पूरे वेब पेज में जितने भी वर्ड्स हैं उनका मैट्रिक्स.
No. This is
Google search.
Yeah, Google search is different. Like they are just using, this is in a large language model. Once you are training, for example, let's say you are training, so you just put a sentence like this, okay, and you expect to generate the next word. Let's say bank, you don't put bank, and you put I swam across the river to get to the other bank. Bank is not there. So now I swam across the river. These are all vectors, v1, v2, right? So you have an x. So these are the tokens that you have. So your x is words 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Or if let's say even the bank is there, like you're just training the network. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are 11 words, and for every word you are using a vector of dimension 300, which you have taken from word2vec or other embedding solutions. So this is your vector, 11 into 300. Now because you got to train it by just having all these elements connected with 300 by 300. So these are the weights, 300 by 300. So all these 300 by 300 are going to be multiplied by this matrix. So you are basically doing the matrix multiplication, but all these W11, these are the trainable weights. Okay, now what happens is that जी इसमें ये पहले ट्रेन हो चुके हैं, ठीक है. हम देखेंगे ट्रेनिंग किस तरह से होनी है. अब ये सारे ट्रेन हुए हुए हैं अभी. ओके, व्हाट वी आर सीइंग इज ये ट्रेंड है. दिस इज हाउ, मतलब आपने चैट जीपीटी को किया तो उसमें सारे ट्रेंड मिलेंगे आपको, क्योंकि इनकी ट्रेनिंग उसने जो की है, इट हैज स्पेंड, एज आई वाज टेलिंग यू, 361 years to train these weights, because they are going to be in billions. So billions of parameters are being trained to give you which understand, and you say summarize this document. Okay, so it is just going to you put the document, it's just going to just learn everything about this, having a picture of that, having all the self-attention, multi-head attentions, going to pass through multiple layers, and just going to summarize. Okay, so all these weights are already being trained. Okay, we'll see an example also in a while. So now these are the different aspects which the large language model must learn to translate it, to summarize it. If there is a question, to answer your questions. Okay, so it has to understand every aspect of the sentence or sentences. So it also has to say swam where to the other bank. It has to know who swam, I swam. So it is going to, so it has to pass through multiple layers, where it is just learning all of this, everything, swam, the river, the other bank. So multiple aspect of the attention of the sentence, because end of the day these are just numbers, algorithms, it has to kind of make sense. So it gets into the multi-head attention. Okay, the multi-head attention. The multi-head attention is where now you have many of these. Okay, so now you have this vector which is n by, so these vectors are, you have n by d, and then you have many these, many of these, and actually you divide them. Let's say these are h heads. So these 300 by 300 weights, let's say 10 heads. So you are going to have 30, 30, 30, and you make 30, 30, 30, 30, 30. So you make them into 10 heads. So you may have 20 heads, may have 50 heads. So you divide these weight matrices into as many heads as you want to look into the different parts, and they are going to do same matrix multiplication, same scaling, same this, and ultimately they are going to have multiple V1s, multiple V2s, as many number of heads. For example, here 1, 2, 3, 4. There, these are 4 heads. So you have one head, second head, third head, 4 head. If there are 4 heads, so let's say 10 words and 330, 30, 30, 30. So now this is how. And all you have to do is just concatenate them together and put them into one. So it becomes just one, and that is what you pass to the next layer. So this is the multi-head attention, where you concatenate all these heads and then pass it through a linear layer to have this. So here is the same thing that you are going to get, but now through a multi-head attention. As it says, their heads are H.
सर मल्टी हेड जैसे कि प्रोसेसिंग को काम
नहीं, मल्टी हेड इस वजह से कि वो जो उसकी अटेंशन है ना, सेल्फ अटेंशन, वो कभी है रिवर स्वयं इस पे, कभी है आई स्वयं, कभी है आई दी रिवर दी वो, समझो. सो जस्ट टू गेट दी अटेंशन, different aspect of the attention, you do the multi-head. So multi-head attention is through these matrices, where now these matrices are D into D by H. Okay, as I mentioned, number of heads. So every matrix will be 300 by, if there are 10 heads, 300 by 30. These are going to the matrices. So once you compute an output through this whole thing, so your dimension is going to be D by H. Okay, D by H, D by H, and then you are going to just concatenate, put them together, and this becomes your Y, D by D, and then you again multiply it with the linear just combination of, and you get the value. So that's what we have been doing all along. So this just shows a 3D picture where you have, now perhaps this also makes you understand, like every word is a vector of same length, vector of same length, vector of same length, okay? And these are the weights for the queries, the keys. And you are going to, these are multi-head, head 1, head 2, head 3, head 4, head 1, head 2, head 3, head 4, head 1, head 2, head 3, head 4. And this gets multiplied, and here are the keys also similarly, and you get the softmax, and then the values as well. So you just multiply them. This is called the linear layer, and you get the final value. So here is an example, a hypothetical example. It says G.
Sir, how the number of heads are defined?
This is also based on the application and by just hit and trial, that how many heads should you have. सही है, कोई यानी कि there is no mathematical formula to define that how many heads should you have. So for example, ये एक example है. I went to Stanford CS 224N and learned. And once you do, the query is on learn. This is your query word. So everything is, it is giving like some association, but more to CS. Okay? The way it is, and so this is all that we have seen, that this is how it happens. Now comes the very important question which I earlier posed, that till now you are just working on words. Word is a vector and their relationship with each other, and there is no really consideration of the sequence in which these words are falling, because that sequence is also very important, because sequence would tell you whether a word is a verb or it is a noun. Right? Because as I say, I love Pakistan and Pakistan is my love. Okay, so is where it comes into the sentence becomes very, very important. And this is, I don't know how like they thought about this, and it actually worked. So there are two things, that how somebody could just think about that, how they are going to put a sequence into a sentence. and where the sentence is considered in parallel. Everything is in parallel, okay? And it's just a magic of the neural network that it will learn. Somehow it will learn that this is the sequence. So this is what they tried. They said, why not to do positional encoding and right on the onset add something in the vector, another vector of the same size, call this a positional vector. Right? A positional vector. Add in every word, convert every word into a vector, then in this vector add another vector which is the positional vector. And neural networks somehow will learn that this vector is the first word, this vector is the second word, this vector is the third word, this vector is the fourth word. Okay? So this is what they do. So they use this expression for positional encoding. Okay? So this is positional encoding, and I'll show you some of the because if you look at this, this is the dimension and this is index. This is first position, was first vector, second vector, every vector is different. And perhaps it gives you a sense of progression. Okay? This expression gives you a sense of progression. So basically these are the two cosines which you use. One is a sine position, this is 2i and 2i plus 1. So first number is from this expression, second number is from this expression. So these are all the sinusoids that you are going to have. This is position, your first vector. It is 0, 1, 0, 1. So it is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and depending upon the length. This is your second, 0.841, 0.540, 0. This is third vector, fourth vector, fifth vector. So all these are going to be different vector because now you have this d dimension. So I'll just make sure that you have different vectors for the sequence that you are creating. And so you just go and add. So this is how are you. Let's say these are 3 words, and every word is represented by 4 element vector. Okay, 4 element vector. So you have to create a positional vector for every word which should have length 4. Similar to this one, 3 by 4. And this vector you add in the first word, this vector you add in the second word, and this vector you add in the third word. So you're kind of corrupting the original vectors, right? So those are like you learned and but then you add the positional encoders values, and somehow the network would able to understand, because you're just doing this again and again. You'll understand there is a sequence. Actually there is a sequence. This word comes first, then this, then this, then this, then this. Okay, it will somehow understand. So this is what now the self-attention is, that you have the chef who blah 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 food. It goes through the self-attention, then the feed-forward network, then the self-attention, then the feed-forward network. And you may have different multiple heads. Here it is attention weights for learn is this, but then on another head it may be this, and on another head it may be this. Okay, that's the idea, kind of, that you have now multiple heads. It is somehow it's saying who learned, I learned. Okay, how I learned, taking the CS. So because you may be asking question in this sentence, who has learned anything? So the language model has to answer you that he has. What has he learned? So say it has learned computer science. So somehow this model has to completely understand all these sentences which are there for you to ask questions and he to reply you. Okay. So this I really like that here it says so many books, so little time. Okay. And that's what I started our discussion, that this little has to be colored with the color of every word in the sentence. And it just kind of depicts that, yes, this little has now the essence of every word in the sentence, because going through this whole process, this is what has happened. And so all matrix multiplication, positional, you add positional encoding. So this is how you have the positional encoding added into this, okay, and then you multiply with linear layer, you get the query, and you get the keys, you get the values. So here is the learnable weights 3 by 3, 3 by 3, 3 by 3. And this is positional embedding, means the word and the positional vector together will give you positional encoding. So the dot product, so we have seen all of this, and this is what the is going to do that you have all these matrix multiplication. This is the final. Once you get a D by D matrix, so you multiply it by D and D by N. So you get N by D actually, it's value and then this. So same thing. So you have this positional encoded words multiplied by, they call this a linear layer, where they are trainable weights giving you queries, key values, but that's kind of matrix multiplication, scaling, softmax, and then the value comes and then you get the answer. Okay. So in LLM, obviously, this is how the LLM also works, but then there are multiple layers of transformers. Okay. And every layer is going to learn something more. And this is what people are, as I mentioned, trying to understand in the explainable AI. For example, this is a poem by a Nobel award-winning poet. It says, "Early one morning, the sun was shining. I was laying in the bed, wondering if she had changed at all, if her hair was still red." Now they are just taking things from the internet and they're feeding, and they are saying whether the network would come with red or not. Okay, and remember, it's so unlikely that it will come with red, because bed came so early and there is hardly any relationship with bed and red. So somehow the network has to learn, no, it's actually poetry and it has to rhyme, and in order to rhyme, the bed is with red, so it has to learn all these things by somehow. Okay, so this is, we know the word embedding, and so this is like the network which you are feeding, and you are feeding everything but not red. Okay, and it has, you have bed and red has to be somehow, it has to learn. And this is what the self-attention is doing. Okay, self-attention is saying that these words have this. So these words are kind of has more attention. Bed, here was still, to predict red. Okay, still, bed is the most important. Bed, red, and then perhaps other words have little to do with this prediction. So now you are training. So the large language model is just training itself, and it just get this whole thing, poem from somewhere, and fed it to its network, and it'll see whether it can get the red or not. Okay, so it starts training. So it says, okay, still, okay, this is where it has to train all these. Usually this is our feed-forward network layer, and it says it should have red, but once it actually is training, it says brown, for example. So there is an error. Okay, because it should have been red, it said brown. So it will take that error and feed back into this, so that all the tunable weights will tune it themselves, and until that it starts saying that it is red. Okay, pointing. And what is the output? Output is a vector. That's the whole beauty of this, is that all you have to find out is a vector, which in this vector space should point to a space which is red. That's the error. Okay, so it is pointing to brown. Brown is another error, maybe very close to this red, because end of the day they are color, red and brown. So it says brown, and say no, move more, move to the space which says it is red. So say this is the error. Okay, this vector and this vector has this error. Feed the error. Move this vector a little more so that it says red. So the weights gets adjusted, and now this vector says, oh, this is red. Okay, it says yes, now it is fine. It's saying red. So this is the training part. Okay, And obviously just training on everything on the internet, just you can just imagine, okay, and how many weights are to be there where you're also bypassing. It's very difficult to explain that how this whole thing actually work, but they put so many trainable parameters that they just make it work. Okay, so here is so this is the, so they have this still and what other words are contributing. So still is not still, it is a combination of contents which are these. So still is, was, here, her, so it will have these, okay. And then changed, then every word you will find out now has the essence of the content of the sentence once you are doing self-attention. And now once you have this and this is fed into the predictor, it will definitely, if it is trained properly, is going to predict. Okay? So this is how then it works, that as you feed in a sentence, okay, it is, if once it is generating the source code, it is generating, right? You have seen, like you say, generate this, it'll just word by word, it starts generating the code. So it is how this is, it is a lot of fun. Who was the 16th president was, it has learned somewhere. Okay, it'll just bypass, get to that layer which says was Abraham Lincoln. Okay, but Abraham Lincoln also is a vector into that vector space. So multi-attention, and then definitely do normalization, and these are the feed-forward transformation like a neural network. So it's like a lot of weights that you got to train, and then you get the final prediction. So a transformer, this is good. That first layer of transformer, for example, has made it learn that wants is a verb, okay, and cash is a verb. So they are the verbs. The second layer has made it understand that once it is saying his, it is actually John. John wants his bank to cash the, okay, and once it is saying bank, it is actually a financial institution. So every layer is just helping this whole thing to basically understand the content, so there are, so the large language model, you have transformer and transformer and transformer and transformer and transformer, and then multi-layer perceptron, which is going to give you that this should be the next word. Okay? Out of thousands of possibility, this is the most appropriate because it would have understood the prompt that you have given it, and so say, okay, this is what it is, this is what it is, and these are all the trainable parameters, and only the perceptrons and their hidden layers, like these are, I think for one of the large language model, and it says these are 175 billion parameters, where it has output layer has these many neurons, output vector has, because it says you can put this bigger length of document, and remember every word in the document is going to be a vector, it's just going to travel upward, okay, and all at the same time, they all at the same time is going to travel upward. And so this is, people are trying, and this is a very important area in AI, and many people are working in trying to explain that how this whole thing works, okay, and they still say that they can like figure out this self-attention or multi-head attention, but not what the weights are doing to them, what the weights are doing to queries, what the weights are doing, because the billions of weights, how can you figure out possibly that how they basically make you just generate a sentence, just generate a poem, just generate this. So it's kind of impossible. So here is like there are softwares which would just help you to understand, okay, this is layer 0, attention, self-attention. All means it's just going to go to every word and it'll show you, you can stop anywhere and see that how this whole thing is actually working. And then there are the entire model, like every, so these are the heads, multiple heads and multiple layers. Taking the same sentence up, and then attention head view. So you can have layer 0 view, and here is the neuron view, what neuron is going to do, okay? So here is, if you see, this is the word, this is the query matrix, okay? So here are the keys, here are this, and because this is the word and you are computing this is softmax, we are the probability. So you see this, I have it better shown here. So this is just layer 0, head 2, this one, head 0, head 1, head 2, head 3, head 4, head 5, head 6, head 7, head 8, head 9, head 10, head 11. Okay, so 12 heads. So layer 0, layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. So these people are trying to understand it more and more, that how this whole thing is working. And so this is the model view. And here is just one attention head view, that you have everything, is finding out that how it is, every word is related to every other. And this, the thickness of the line shows that how they are kind of related. And here is the vectors, like I, and this is a vector, I went to, once it has been multiplied with the matrix, WQ matrix. This is once it has been multiplied with WK matrix. This is once. So, and this is the value is not here, but this is WQ. This is, after your X multiplied with this, it becomes this matrix. After your X multiplied by this, now you can see they are different. People are just trying to understand why the same matrix has become different. As the query is different and the keys are different. Okay? And now they take this query and then multiply it with everything to find out its softmax with everything. So it is that, and then they take their dot product, it becomes that, then they take the softmax. These are the probabilities. This is, the color shows that how it is related to different things. Right? So this is, people are just building these tools so that you just try to understand that what is actually happening underneath, why it is working, and so that's what it is. Okay, so now it's everything. Now you see everything changing, right? The shade tells you the, so this is what is happening in one layer. Once you do the softmax, then you have to multiply the softmax with the values, so that, and then you get. So here is the same thing, interesting. So you can just see any, so this tool where you can just play with this tool, you can go to the address, I think I've written its name somewhere, Viz something. Okay, so here is, so same thing, okay. So heads and layers, and so same thing. So again, it shows you again the same thing, so that just makes your concept clear, that how this whole thing is working, kind of.